If you can't, let me know. That's the only way to do this. Um, so, anyways, we are here, but we didn't always know that. This is going to be a whirlwind. I'm not going to hit on, you can't. 2,000 years of astronomy hit as, but like, I wanted to kind of like, this was a, 30-minute talk or less for the UTC star parties. I went 35. But it's just a crash course in it. But it just was like, I put things into perspective. So, you know, we've always been looking up, right? I mean, even tens and tens of thousands of years, I'm sure animals as well, but as far as humans are concerned, we've looked up, and compared to today, we were so much more in tune with things back then. We didn't have all the lights and just the internet, everything else that keeps us preoccupied to know space. We were into, this is where you lived in this. You looked up and you saw that sky every night. You saw it change every night. And so it's not like this is anything new. We've been doing this for a long time. But actually recording it and really trying to understand it is probably more what I really kind of I focused on here. So I haven't been here. You've been there.
I haven't seen this.
Yeah. So Chaco Canyon's in New Mexico. And I went to grad school in New Mexico, but just never made it here. But like 7,500 years ago, a star went boom. It's M1. It's the Crab Nebula. And, of course, it finally, it happened 7,500 years ago, and we finally saw it, about 1,000 years ago, once that light finally reached Earth. But some Chinese astronomers actually did recognize it. There was all of a sudden this big flash and this new thing in the sky, and that was actually recorded, that we know that, in history. But in Chaco Canyon, this is a neat perspective. You're looking up a cliff, and somehow underneath this cliff face is this little guy here, the moon. That's actually an eclipse, I think, or a comet.
If you look, it's got a tail.
Yeah, that's so. And the ancient Pueblo in the area was around that same time when the Crab Nebula was also recorded by the Chinese astronomers. So they actually think this is a recording of that supernova. All of a sudden, it had to be incredibly bright. So even 1,000 years ago, it in tune enough and recorded it. And on top of that, I can't go into the full description of this, but they even knew ways of placing rocks that had gaps in them, and depending on where the sun was in relation to us moving around it, they were able to pinpoint where they were in the solar cycle. Are we in the spring or winter equinox, or fall, winter, or the spring and fall equinox, summer solstice or winter solstice? From what I understand, these have moved, I think, at one point, and I don't know if they put them back or not. But so this is just one example out of who knows how many I could probably pull off. But I just think this is in the U.S. and it's just kind of neat. Even 1,000 years ago, we're still in tune with it. May not understand why, but we've always we paid attention. And so you think about like present day Iraq and Syria's, that the Mesopotamia area where the Babylonians, when I think ancient astronomy, that's kind of the first thing that pops into my mind. I don't really know a lot about what they did, but they were really focused on astrology and zodiacs, of course. We're very familiar with those. But they also were able to predict eclipses, and they knew a lot about the 5 planets that, you can see the roaming planets, across the sky. And so even, 2,000 years ago, we're starting to really predict things and try to understand what they're seeing in the night sky. Told you this is a whirlwind. So then comes Ptolemy. So think of Alexandria, Egypt area. So about 2,000 years ago, a little over 2,000 years ago, he was pretty much the first influencer. I mean, there were others, but like when it really comes down to it, what he put down in writing and about his thought about we were an Earth center. So when your perspective, when you look at it, if you really don't, I'll get into it in a second, but like it makes a lot of sense that everything goes around the Earth, just the way things, that not that us moving around the sun is moving around us too. When you look at it, especially from, this is prior to calculus and, computer models and everything else. But like, he pretty much was the start of it all. And people referenced him in his work. Really, he was the predominant thought for like 1,500 years. It also really fit the times too. I mean, you think about that 1,500 years, how influential the church is. The church was very adamant about everything revolving around the earth and this perfect universe around us. It fit really well. And so it really was. This was the main literature for influencing how people thought about the universe and where we were. So we were the center of it all. So then there's Copernicus. He wasn't the first person to actually go, hey, no, it's really heliocentric, not Earth-centered. But like he really was the one that put it down and did it right at the end of his life too. Like he published this like right at the end and goes, good luck. I don't have to deal with this now. I'm not going to fight the church or anything on it. This is what I believe. But like he really set things in motion, is going, no, when you really look at it, he didn't have the perfect model, but it was like, no, we're really going around the sun. Things aren't moving around the earth. And he was really influential on that. And he was kind of like that catalyst that started where we're like pushing, others were taking that and running with it. That, okay, maybe we do go around the sun. And then, so you had the Copernican versus the Ptolemaean, kind of thought process there for a little bit. So when I think of like that sun-centered, universe, I always think Copernicus, even though he wasn't the first, but he really was that main influencer on that. So not too far after Copernicus, you have Tycho or Tycho Brahe. I've heard both. You laughed at that.
Yeah. I thought it was Tycho for years. I saw something on YouTube and the guy was calling it Tycho.
So I've always in my head Tycho, but maybe that's just because I see that's how I want to pronounce it, and it's not really. But he was a Danish astronomer, and he was obsessed with like finding order in everything. And he came from an affluent family, and he was was getting paid by the king, and like he had all these this little island he set up on, and all these contraptions he had hand built to just meticulously measure the location of stars and to plot them out. And we wanted to understand what's going on in the universe. And he was kind of like that first person to have that. And then at one point, towards the end, Johannes Kepler, who was mostly just a very smart mathematician, came under his tutelage. And Brahe was very protective of his information, especially he did a lot with planets too, and measured. I mean, the stars moved, but man, the planets really moved. And he had all this meticulous data on that, and he just wanted to kind of like hoard it. Somehow Kepler was able to kind of coerce him. It's like, can you at least give me one planet so I can work with this data? And it happened to be Mars. And fortunately, Mars was like the best planet to give him to be able to use. And so if you're familiar with Kepler, he came up with the three laws of motion for planetary bodies and gravity and how they move in ellipses around others. And but he was able to use all those measurements from Tycho. I'm gonna call him Tycho. To develop all that. And so he's kind of like the first person to kind of put all that together. And we still use them. We still teach that in astronomy classes. And we use them for other things too now. I mean, it's not just the laws of motion for planets. It's so we're starting to finally move into like, we're measuring things more and we're understanding how things work. And it's not just going, ooh, pretty stars and they move. And boy, we're thinking about the mechanics and the physics behind it and what's really moving the universe. Of course, we still think we're just pretty contained in our own little Milky Way at this point. And then there's this guy. So it's about the same time as Kepler, but we now have this new thing. Tycho had his measurements, and he had all these instruments for measuring where stars and planets and how they moved. But he didn't have a telescope. Kepler supposedly had looked through one. I don't. There's like documents that are contradictory on whatever, but Galileo for sure. He didn't invent the telescope, but there was is it? I think it was a Danish. Wasn't it? I think it was a Danish lens maker that made the first one. He copied it, made it better. If you can call his telescope great, you see these things. I mean, they were awful, but they were still amazing for the time. And so he was really the first person to document pointing that thing off into space. And it wasn't first Jupiter. I think it was the moon first. And then he moved into Jupiter. And once all of a sudden, we think we're the only thing in that we have this perfect harmonious universe where everything is circular and everything is perfect. And then we're the center of everything. But then there's this other body, Jupiter, who all of a sudden have these 4 bright little dots that change throughout the entire night. And every time he would go back the next night or even throughout the night, those 4 little dots, not being stars, had to be moons moving around another body. That changed everything. So this perfect universe has changed. And all of a sudden it's like, wow, those planets, that we could are actually have their own bodies going around them. And it was very controversial to say the least. Along with Copernicus, who had his own issues with the church, he ended up passing, away right after he put this out there, and it's like, but Galileo didn't. He ended up in house arrest towards the end, and at first the church actually really supported him, and then in the end, it really went against things, and he ended up in a losing battle on that. But it really was the start of things with the telescope. And so we're about 500 years ago. 400 years ago. It's the first time we've pointed a telescope towards something. And, it was rudimentary, but it was still the beginning. So I think this is kind of neat. I didn't, actually researching this, I didn't realize how much Halley was involved with so many other things. I knew he was, but I didn't know what he also was involved with. You think Halley is just because of the comet. He's only famous because of that, because he actually recognized that the comets were coming back. That comet was coming back every 76 years or whatever it is. And that's why he has his name on it, and all of a sudden he's famous for that. But in reality, he was an incredible astronomer and mathematician. This is what's kind of neat. So he went around to see it, but he was like, if you actually see Venus, it comes around twice every couple hundred years, where for a decade it goes across the sun twice. And if you see where it hits here on the sun and then over here, you can calculate that. and get distances to something. So up until then, we could see that we understood motion and everything, but to actually get the distance to something, he predicted that if you saw that, you could figure that distance from the Earth to the Sun. That's revolutionary. And then the other thing he did was with Ptolemy is that he noticed that there were certain stars that don't match what they were back then compared to where they are now. And going, wait a second, stars move? They're not fixed points. They don't look like they move. But if you look at those calculations and whatever, it's like, hey, our stars move too. And we kind of came up. That's where the term proper motion was for their movement of stars. So I thought that was kind of neat with Halley. And of course, that's a picture by Barnard, one of his plates for Halley's Comet. That's when you send a satellite to it. That's what it really looks like. I think that's fascinating. We're used to this. They're beautiful through a telescope, but it's just this little fuzzy little dot. And sometimes you get this beautiful tail and so forth. But Halley would lose it if he saw that. And then we have the Herschels. What's funny about this, I just read a book last year about them, is that he was a musician. And like he wasn't even, he just kind of got into that later in life and just ditched everything to become an astronomer. And built this monstrosity of a telescope. I mean, blowing Galileo, it's like this is only a couple of, 1609, so less than 200 years after Galileo. This little teeny tiny refractor he has, it's like, no, we're going to build this. So they were they Dutch? They were German. Yeah, thank you. I've read too much. That's the problem. You get things kind of messed up or mixed up with that. But they ended up moving to Britain. And they worked together as a team. It was a brother and sister. And so he would go out there and work the telescope, and he would have helpers out there to move it up and down, and he would sweep the sky with it. And she would be sitting in like a bedroom window where it was warmer, and he would yell stuff at her, and she recorded everything. So he was the observer, and she ended up in the beginning being yes. Yeah. So she was really the one that carefully was writing everything down. She ended up becoming her own. She was the first paid astronomer that we are in history that we're aware of. So the King of England ended up at one point paying her as well to be an astronomer. And she did things on her own. I think she even identified a comet on her own once. And like she became her own astronomer at one point in time. And so his measurements, that is the first picture sketch of what the Milky Way supposedly looked like. And that made waves back in the day. It's like, ooh, this is what our Milky Way is. It's like, wow, this is where our place is in the universe. And I found this online. Somebody went in and took that and overlaid it where it was in the galaxy. So from our perspective of our sun off on the limb of of our galaxy, this is kind of where that is. So we're at least getting somewhere. We've moved from just, here's some stars, there's some movement, planets. All of a sudden we're mapping our galaxy, and we're realizing how much bigger it really is compared to, trying to grasp our place in things. And during the same time, you'll get the point here in a minute. I'm obsessed with M51, the Whirlpool Galaxy. But it plays a big part in history, though. It's small, but it's close enough to us, and it's just been documented a lot. But Messier actually, at the same time, was mapping out and drawing things as well. Of course, he only cared really about comets and not really about the other things, but he was still keeping an eye on it so he could ignore them if he ever saw them. That's a fascinating story with him. But he's actually located and noticing these things that are spiral nebula. I don't know the galaxies. This is our Milky Way at the time. That's the best estimate of what our universe looked like and where we were at in it. But we were noticing these little guys, and this is neat too. Like these weren't mirrors in the what you think of. It's polished metal. That's what they had back in the day. So they would have to go in and it would get corroded and they would polish it up again. I can't even imagine what it took to make those. It was not easy. It's not even easy what we do with glass and mirrors and what we have up there, let alone trying to make it out of metal. But that's what it was. It was polished metal. And they did amazing stuff back then with that for a reflector. So it's a reflector telescope. You notice I even skipped over Newton. Can't fit everybody in there. But he didn't. But, he did work on the reflector Newtonian telescope. So you've got this telescope here. So it's about 18, I think, inches or something like that. 18.7 inch mirror. We got a 20 and a half inch upstairs. Ours is bigger than his. The design, luckily with us, with that Cassegrain, could shorten it up and it didn't have to be so big and long like his. But that one up there is actually even more powerful. But then I think I haven't looked it up to see somebody pronounces it. So the third oral Ross, I guess, probably. William Parsons was another pretty well-to-do guy. And he's like, I'm going to build the biggest telescope I could possibly build. And he did. This is brick. That is a 72-inch metal mirror. And he's like, I'm going to build the biggest telescope there is. And he did. And I guess the foundation and that structure is still there. The telescope, I don't know if it is or not. I can't remember. I remember seeing a picture of it when I was looking at this. But it was called the Leviathan of Parsonstown. But you think M51. So here's Messier. And I don't know. I can't remember what telescope he used for that. All of a sudden with it, you go from this big of a mirror to one that's as big as me. I'm 74 inches ish. That's a big mirror. That's what M51 looks like through his eyes. I just can't imagine looking through that and seeing that with this old metal. I just think that's really phenomenal. But all of a sudden it's like this little faint little spiral nebula is getting, this thing has got detail. I mean, look at all that. And he even looking at this going, that may be another universe or another galaxy. It's like, we may not be alone in this thing. That just looks too much like what we might be in. And we're finally getting a glimpse of some, but they were still nebula. We still weren't quite there yet. But the big kicker with some of this stuff is like we can make all these observations, but if we can't figure out distance, that's the kicker. Like, ooh, is that a nebula? Is that another galaxy? What about all our stars that are moving around? And what about the planets? We had that parallax, which I'm going to talk about here, like, where you see where the transit of Venus is across the sun. Point here, you can triangulate. I can do them. You can do that math. But that's okay, great. That's for Earth to the sun. What about space? Unless something's close to you, parallax was something that Frederick Bessel was the first. He wasn't the only one that did it. There were a few other people at kind of the same time, but he was the first to publish it of parallax. So as this diagram is showing, so that's the sun, and that's our Earth moving around. Perspective-wise, a star is going to look like it's moved if it's close enough to us. As we're going around the sun, that star moves just a little bit. This is kind of an exaggerated, but it's the same thing with that Venus. You can measure that. So if it is close enough to us, and I think I did this in the thing where you're like, you put your finger out here, you put it out here, and you change your eyes. It kind of moves a little bit. You bring it in here, it's a big difference. So if something's too far away, it doesn't matter. You don't have if it's too far away to really notice that measurement. But if it's close to you where you can do this, you can measure that. And so he did that for some close stars. And it was 61 Cygni, I guess, was the first one. So we're finally, it's like, okay, we can get distance from that. And and finally published that first distance to a star. And this is not working I'll try it in here, but it didn't work when I did it earlier. Oh, it did. This started off at 10,000 or 100,000 years ago This is what the Big Dipper does. And we already passed it. But that was a simulation of like 100,000 years of perspective of Ursa Major. So if you didn't see that, I'll start it again. So you see the countdown up there? So we're about to get to where we see it now, right there. And so in 100,000 years from now, those are what those stars are going to look like from Earth. Yeah. So they're moving, but so slowly that we'll never notice that in our lifetime. I mean, I'll look up and the Big Dipper's always going to look the same, and I'm not going to be around in 100,000 years. They have movement, but we just don't recognize it. And if they're close by, it's the only way we can recognize that with these old techniques. But somebody did that. So we do have motion. So we're really starting to slowly work our way into understanding what's going on. And then you have the Harvard computers. This blows me away. I've read several books, and I did finish the Glass Universe. Such a good book. So if anybody is interested in learning about this, the Harvard computers, these were the women that basically, this is a lot of them was the only way a lot of them were unpaid, but it was the way that they were to go in and actually contribute and do something, rather than being at home. Because that's what you did back then. You weren't allowed to be a scientist. But Edward Pickering, and he got them on the cheap. So the ones he did get to pay, he got them cheap, but he did get them in. And they were incredibly just brilliant women that were a lot of them mostly with mathematics backgrounds and so forth. So we're finally at this point in time, by the late 1800s, photography. So astrophotography starts becoming a thing. So you've seen, the glass plates and stuff out of here. Some of those are, 100 years old. So they were taking glass plates and taking those and making measurements and providing that to the other astronomers. But a lot of them were, they're really smart. They were doing some things on their own and recognizing things even before passing it on, to their male cohorts. So, and I can't talk about all of them.
They were cataloging stars. I don't think
Yeah.
Stars.
Thank you. Sorry. Yeah. So they were basically, you got a plate. So you got out here, you got all these different stars on there. And they were so good at recognizing magnitude. So they were able to see which ones are brighter and cataloging all those, cataloging exactly where they are, where their positions are, and just generating this massive database. Thousands of these glass plates from all over the world were coming through Harvard. Harvard was the place back in the day. They had a place in Arequipa in Peru. They ended up having another place in South Africa for a bit, and they were shipping all those plates back, plus in the U.S. And they were really the ones building that catalog. And the two that I would just want to Henrietta Swan Leavitt, which is this lady back here with the magnifying glass, and Annie Jump Cannon, she's right here in the foreground. The big thing with, all these women have their things, but Leavitt is the one I want to talk about, is she ended up taking over the group after Pickering for a little bit and was in charge of the women for a while. I could go into it for long. It's a good book. But Leavitt's kind of she was in charge of looking at variable stars. And so variable stars are ones that change in brightness. And they could either be short period where like over days or weeks, stars naturally fluctuate in brightness. And she would record those. So a lot of them were from down in the Boyden Station in Peru. So we don't get to see this here. This is the large Magellanic Cloud. There's a small one too. So this is a modern version of it. So this is one of the original plates that she would look at. Imagine looking at every single one of those stars, figuring out the magnitudes of them and trying to figure out which ones change. They were good, and she was really good. I don't have the patience for it. But they would literally go in here and mark, and I got to blow up. they would take one plate, then look at the next plate and compare them and see if they change. It's amazing. So this is her handwriting. They'll go, so here's one that was a 10.7 at one point, and then maybe a week or two later, it's a 10.5 or an 11.8 to an 11.6 magnitude, and seeing those changes and recognize, and then over time realizing, okay, this one goes from an 11 to 11.6 back to 11 over this certain amount of time with these variables. And so they would record those. And the neat thing about it is that she recognized a pattern. So those short-term ones, every like days or weeks or so forth, they change in brightness. They were called Cepheids. That the longer period ones, or got confused here. Those they where was I going with that? Had longer period than the dimmer variables. So there was enough pattern in it. I'm sorry. It's been a long week. But like there was a pattern in how those changed. And she plotted those. And if you could realize, if you knew the distance of those and knew how those changed, and by this plot, you could get distance. So you could, these Cepheid variables, if you found those and could measure those over time, you could use that to get distance. That was game changer. If parallax was the one, but you're talking things in the small Magellanic Cloud, which is another galaxy, kind of a small one attached to us. That's pretty far away. But because they're Cepheids and you could measure with these trend and get those distances, man, that changed everything. And so it was this period luminosity law that really started that. And that was, we're talking 1838. So we're still less than 200, or no, she's early 1800s or 1900s. So this is like less than 100 years ago, or about 100 years ago, recognizing this. And so Harlow Shapley was another Harvard. He kind of took over for Pickering at one point. He was off working over at Mount Wilson, and he really loved globular clusters. And so he would map those, and he would identify Cepheids in here, and took Leavitt's stuff and started mapping distances to these clusters and go, wait a second. I know where, and mapping where they're located in relation to what we think our galaxy looks like. And these are where they are, and using those Cepheids to do that. And he was kind of the first person that realized that, man, for one, Earth isn't the center of the Milky Way galaxy. Whoa, this is, if you're looking at it edge on, we're way out here. And he was the first to kind of point that out just by measuring out where these clusters were and getting those distances and so forth. And they all were kind of clustering around the constellation Sagittarius, which we now know is where the Sagittarius A star, a big black hole that's in the middle of our galaxy. He was not exactly dead on as far as his measurements, but boy, he exploded it like 10 times bigger than what he originally thought it was, or something like that. Actually, it is 10 times. So, but like we're starting to finally, like, things are exploding at this point. We're getting distances. We're realizing we're not at the center. Our Milky Way is just, it's getting bigger. It's like we're really seeing how things are moving around and where we're at by this point in time. And that whole thing with Cepheids with Leavitt really was that kicker that really started it all. And so the next person to kind of take that in is where I'm going to kind of really explode here to finish this thing off here. The star that changed the universe. And this is the truth. So this is actually a sketch by Messier of Andromeda Galaxy. And then here's their kind of little host galaxies off to the side here. This is the very first, I guess, known image of Andromeda in the 1800s in 1888 from one of those glass plates. It was still a nebula. There was, we didn't know that, there was speculation that this is another galaxy, but for the most part, we think there was a huge debate. Shapley with his globular man, he was adamant that we were an island universe. We were the island galaxy. Those little things are just nebula that are out there. And most people were, but there were a few people like, that might be another galaxy. But without knowing distance, it's like you can't prove that. But because of Leavitt and eventually Shapley, because he went and did some work on it himself, this changed right here. Edwin Hubble. So that's a whole nother book. He was an interesting dude. But he was working out on the 100-inch Hooker telescope out at Mount Wilson, taking photographs, and he just fascinated with Andromeda and went back to that several times and going, you know what? That's a nova. So they put it in. That's a nova. Put it in. There's something changed. You go, wait a second. Oh, there's a third nova because they're changed in brightness. It's like, because that wasn't there before. Well, going back and looking at the plate again, a new plate, it's like, wait a second. Nova. That's a Cepheid variable in another galaxy. The 100-inch Hooker telescope was so big and revolutionary at the time that you could get individual stars in another galaxy. Didn't know it was galaxy at the time. But this one star in that galaxy or that nebula, the Andromeda Nebula, was like, wait a second, Henrietta Leavitt, Shapley, they've got ways that I could measure that. And he did. And so he measured that thing and saying, hey, because of that Cepheid, and this is his plots, that's got to be at least 900,000 light years away. He was off a little bit. He was like about a third of the way there or so. It's like 2.5. But still, that more than, Shapley saying, here's what the Milky Way is. This is how big we are. And all of a sudden, you're talking another million light years away because of that one Cepheid. That is not within our Milky Way. All of a sudden, we went, and that's 100 years ago, that we went from, are we an island or are we not an island? All of a sudden, yep, those little faint spiral fuzzies, they're other galaxies. And so thanks to Messier, he didn't care about them, but we knew about them. We've seen them on the plates, but they were just nebula at the time. And all of a sudden, thanks to one star, we're not alone. We'll see if this works. If not, I've got the video. So this is us zooming in on. So this is what we look at. This is a full-blown our Milky Way. That speck right there is Andromeda Galaxy. So that's from our perspective of this one galaxy, and we're able to locate one star within that. And this video zooms in on it. It's just to put it in perspective. If it freezes too much, I have it downloaded. Yeah. Let's do this. People online aren't going to be able to see it though because I'm. Oh, there's music. I'll mute that. There we go. All right. They can see it through the camera. But just to think, this little faint fuzzy, with this massive telescope, to be able to go in on this and find one star, even to recognize that one star varied enough and it changed everything. You see it yet? That's crazy to me. just to think that like just one random star in another galaxy and it's a faint fuzzy, like to be able to recognize and see that change. And it took 100-inch telescope and photographic plates to do that, and somebody that could recognize it. He was an eccentric guy, but man, he was really good. So back to here. Hopefully my online people can still see. So we'll skip that. I had a bad feeling that was gonna, there we go. So just to kind of, this is a neat kind of put it into perspective. Told you I'd talk about M51. Top left is William Herschel, and then you got Lord Ross here. And then now, this is what we're used to seeing. We're spoiled nowadays. I see, I was around when Hubble, a lot of us were, when Hubble first put up its images, and we're seeing these massive, beautiful spiral galaxies. And now we're just inundated all the time. We're just kind of like, take it for granted. It's like, oh, of course, that's obvious. But it was like 100 years ago, we didn't even know that. That's just, to me, mind-boggling. I wake up every day, and of course I see everything from the James Webb and everything that else is coming out there, and it's mind blowing, but you're not astonished by it. Hubble would lose his mind. Clarence T. Jones would go nuts. I can't even, to even realize and to see some of these images. This is one of the Hubble images. So just, this is one of those deep field, they pick this little patch of sky that has nothing in it, and then all of a sudden they get this back, and that is thousands and thousands and thousands of galaxies in this little teeny tiny little speck of the sky. I remember when that happened. Talk about you're thinking with these old telescopes, these old metal mirrors, and you're looking at it, and you see this little faint fuzzy here, and you're there, and you still have no idea where you are in things, and then you see that, and you're like, holy, and so then you get into James Webb. So there's the Hubble version over there, and this is the James Webb. That's one of the first images that put out that day. We're seeing these warped galaxies, these do gravitational lensing, and again, thousands and thousands and thousands of galaxies. This little teeny tiny little sand grain of a view, and it's just mind-boggling. This is M51 by James Webb. It's in infrared. So we're now looking at the internal details of these faint fuzzies that Lord Ross and Herschel would have no clue what they were seeing. This is really what it looks like when you're looking at these massive monstrosities we're building now. And I can't not, I gotta have to end on the Vera Rubin. I'm actually reading a book on Vera Rubin right now, which is another really good book. That is the biggest camera on the planet. It's, what is it? 8, I don't remember how big the camera is. The mirror is 8 meters, but the camera itself, it's like 3,200 megapixel count. I don't know what my phone is. It's like 12 or something. It's something stupid like that. Like the amount of data, you think about this. This is one picture. It goes, and it is going to do that every night. The entire southern hemisphere in over 2 or 3 nights, it's going to cover the entire southern hemisphere with the biggest camera on the planet. It's going to be terabytes worth of images every single couple of days. And they're going to do that for years. And so every few days, they're going to get a time lapse. They're going to basically have a time lapse movie, the entire southern hemisphere. I can't remember what terabyte versus terabyte worth of data that they're going to have. That is just, they're going to have more data than they want to do with, and AI is going to play a huge role into it. But this is some of the first pictures that they released of that. And that's just one little tiny little thing about that one image. And those are all galaxies. What's ahead of us? I don't know. That's why this talk to me the sequence that. It's just,
we watched the first images,
Yeah,
right?
yeah.
That summer, and they're also, didn't they find an obscene number of asteroids?
Oh, the first
Just
night.
from
Yeah.
the first video.
Yeah.
They're like, holy crap!
like
There's a lot of moving things
Planet
out there.
X, all the asteroids, comets, like, dark matter is a big one. That's what Vera Rubin really worked on a lot too. I mean, there are so many things that they're going to be data from this that it's just, and this is just, there's other space telescopes coming up. They got the very large, ridiculously large, whichever one you want to call it now, telescopes they're building out there now. I mean, they're all doing different things in different wavelengths, and like how fast things are happening and how quickly. I just, to me, it's just like, I don't know. I just think it's really fascinating. So that was it. So anyway, any questions on anything or?
About 1,000.
Yeah, well, I won't be able to answer them, but I'll try. I'm an amateur. I don't know all the deep delve into a lot of this stuff, but just, I don't know, been reading it and you just see this chronological, like, wow, how they build on each other. And like, it takes one small discovery and then it just, where it offshoots. And all of a sudden it was like, we're like this. And I just think it's really cool. So, I would never trade my background's in geology. That is my number one, but it's like, boy, if I could maybe do it again, maybe planetary geology and take a lot more astronomy courses and stuff. Cause this just is cool. So, but that's all I have.
Good job, Kevin. Thank you.
That's it. Thank you.
Are we Team Telescope now?
A team telescope.
Team telescope.
All right. Well, thank you, everybody online. Anybody have any questions or anything online? All right. Well, thanks for joining us.